Good afternoon, everybody. Welcome to a rainy, overcast Wednesday afternoon of Chem 170 with your host, me, Dr. White. All right, hopefully you all got the email I sent out concerning handing in labs. Yesterday's lab is due tomorrow. Remember, each week here is actually more than 2 weeks in a normal semester, just a little bit more. So we work at a pretty fast pace, and please hand in the labs. As I said in my email to you, last semester I had a student, that student didn't hand in a number of labs, got 0 points, and that student's grade was a grade lower, one lower than what she should have gotten if she handed in the labs. The labs are not that hard. They don't take that much time. All right, speaking about labs, something I've neglected to talk about yesterday was when you do melting points, you look at when it starts melting and when it's all melted. Therefore, if you use a lot of sample, that's going to take a lot more time and mess up your melting point. And also, when you're heating it, you want to be patient. You don't want to do too slow and be there all day or too fast, because that will mess up things. Hint. And with that, let's get back to work, unless anybody has any questions. Remember, in my class, in my universe, there's no such thing as a dumb question. All right. Everybody see reaction of alkanes? Thumbs up, people. Thank you. All right. Now, yesterday I was talking about, thank you, both of you, and everybody else who raised your thumbs up emoji. Remember, you can turn on your webcam. Dr. White will make you feel real good and happy. It's a good thing to make me happy. But anyways, we talked about how alkanes or cycloalkanes reacting with oxygen give carbon dioxide and water. Now, it also gives heat, and that's important, but on a test, I'm going to ask for the chemical products, not heat. Now, this is a general reaction, and this semester, I think a couple of years ago, it's been a while, one of my former students counted how many general reactions I taught during the semester, and that number, I think, was somewhere around 50, 52 general reactions. You say, wow, that's a lot. No, not really, because I know personally about 400, 450 general reactions. That's a lot. But what I've done is narrowed it down, and I'm going to be talking about key general reactions in organic chemistry that play a role in your life. And that's the fun part about this course. You're going to learn things about chemical reactions and other things that occur around you in your life. All right, let's go back and look at this. Now, a general reaction, think of it as a roadmap or GPS. It tells you where you want to go. In other words, what products you're making. By the way, it's cold out, blueberry tea from the Republica tea. But anyways, if on a test or in real life, you're trying to figure out what are the products, it's like if we were here, say if we were on campus in Elgin at ECC, and I said, all right, let's get in a car and go to, I don't know, Eugene, Oregon, or Timbuktu, California. And yes, I have been in both of those places. Yes, there is a Timbuktu, even though you see it in Bugs Bunny, it is for real in California. And if you didn't have a map, and if you didn't have a GPS, and you got in a car and you didn't know where Timbuktu was, or where Eugene, Oregon is, what's the odds of you getting there? 0. But if you have a map or GPS, you're going to get there. It's going to take some time. Well, the general reactions are your GPS or map. And if you don't have them, you're not going to get the right answer on a test. So these are things you have to memorize. And as I said the first day, there's a lot of memorization in organic chemistry. Now, what I will ask is the following. If I can spell. And the question would be, give the product or products. That's why I have the S in a bracket, because in some of our reactions, we'll get more than one. This is an example. Some you'll only get one. And how do you do that? Because you want those 3 points. Well, you look at this molecule and you say, well, it's got only carbon, hydrogen, carbon single bonds. It's an alkane. And it could have been, which is not in this case, a cycloalkane. And we're reacting with oxygen, and you learned this general reaction because you memorized it, hint, gives CO2 plus water. So I've got an alkane of oxygen. I'm going to get CO2 plus water. Now, the beauty of general reactions and in organic chemistry, if you have this, and the question would be, what's the product or products for this reaction? Well, you look and say, oh, I'm reacting something with oxygen. What is this? Well, it's only got carbons and hydrogens and carbon-carbon single bonds. It's an alkane. But it could have been a cycloalkane. And it gives carbon dioxide plus water. So if I react this alkane with oxygen, guess what I'm going to get? You're right, carbon dioxide plus water. Well, I better share some fun. So it's your turn to have some fun. And I would ask you, give the product or products for the following reaction. Your turn. See what a nice guy I am? Sharing the fun. And since you don't have your webcams on, I'll use the poll so I know when you're done, because I try and give everybody time to do it on their own first. Boy, it's already Wednesday. Time flies when you're having fun with organic chemistry. All right, let's do this. Now, oh, we're reacting this with oxygen. O2 is oxygen. And what's this? Well, you look and see for what's different. Well, there's only carbon, hydrogen, carbon, carbon, single bonds, and that's an alkane. Or it could have been, which is not, a cycloalkane. And what do you get? And you have memorized this. I'll be subtle. Everybody get the hint? You get carbon dioxide plus water. Therefore, alkane, oxygen, I'm going to get carbon dioxide and water. Now, you do not, and I would not do in my class, so don't, because it wastes a lot of time. You don't have to balance it. Yes, I can balance it. And the only time we would do that in organic chemistry, when you have to determine what we call an industry charge weights to make a certain amount of product, which I've done many times, but we won't do that in this class. Now, keep this secret. I'm going to show you the chemistry instructor's favorite trick on a test. Remember, keep it secret. And the chemistry instructor's favorite trick on a test is put a big, scary molecule. And if you don't know what it is, it's a big, scary molecule. Oh, by the way, remember there are 4 bonds to carbon, and it's now your responsibility when I draw a structure on there, make sure all carbons have 4 bonds. That's 2. Now, one thing I do in organic chemistry, if I'm running out of room, we can put the arrow like this and put a bend in it. We can have that happen. All right, so the question would be, what's the organic product or products for the following reaction? If you saw that on a test and you didn't know what that is and didn't know a general reaction, you go, E. Hopefully you don't go E, but what the, and you're all, ugh. It's a big, scary molecule. No. If we look at that, let's analyze it. There's only carbon, hydrogen atoms, and only carbon, carbon single bonds. So this right here is just an alkane. Big alkane, complex, but it's an alkane. And we're reacting with oxygen. And this could have been a cycloalkane. And if you react out, you've learned this, remember, you've learned this. How do you learn that? Write down alkane, cycloalkane plus oxygen gives you carbon dioxide, CO2 plus water. I hope everybody knows water is H2O. And you do that 5 times. You can use flashcards, but the 5 times works really good. And then another day, do it a couple more times. It's burned in your brain. So alkane, cycloalkane, oxygen. What do you get? Carbon dioxide and water. This is an alkane. I'm reacting with oxygen. So what do I get? If you know the general reaction and how to identify a molecule like this, it's not big or scary. If you don't know this, you're lost. Now, if you notice, I've been writing it underneath each reaction. On a test, some of the best Chem 170 students I've ever had, if you look at their test, under every reaction like this, where I ask you the product or products, they write the general reaction. And if you look at the test of some of the best students I've ever had in Chem 170, they never write that, but I'm sure it's in their brain. They know it. So either way is okay for me on a test, but in class, like now, I will always, for every reaction, write the general reaction so you understand how I'm doing it. All right. Now, one of the fun parts about organic chemistry is it's in your daily life. And every chapter and things I go over, I'm going to include things in your daily life because that makes it fun. So let's talk about alkanes in your daily life. I don't have a slide for this, so I'm going to do it the old-fashioned way, right on the whiteboard. So let's take a look at where do you find alkanes in your life? Now, the first one, methane, which you don't have to know the structure. Well, you do, but for this methane, where do you find it? It's your natural gas. That you use for cooking, heating your house, and also heating your water, hot water heater. They all use natural gas. Now, what's another example of alkanes in your daily life? Propane, and that's for your barbecue. And if you work in a construction site, that's used as a heater. All right, what's another one? When you get to more carbons in the molecule, you find those in gasoline. Gasoline is about 50% of the weight are alkanes, isomers of octane, and some others. Now, if you get really longer chains and molecules, heavier, more carbons, what would be an example of an alkane in your daily life? And that's baby oil. And baby oil is made up of hydrocarbons, alkanes, and a little perfume. Now, it was interesting, something I knew, but a student of mine a number of years ago reinforced for the rest of the class was I didn't talk about it. You know, gasoline is flammable because alkanes are flammable. Well, she was a neonatal nurse at a hospital, but she was coming back to get her master's, and been so long since she had organic, she was required by the program she was going in to get her master's in nursing to take organic again. And when I talked about baby oil before I could say anything, she said, you know, and she said it to the whole class, and I was happy she did, that baby oil is very flammable, and it is. And we tell new parents of newborn, don't smoke, which you shouldn't anyways, but don't have any candles nearby because baby oil is flammable. Alkanes are flammable. And now what if we go to even bigger molecular weight, longer amount of carbons in an alkane molecule? Well, I'll use a trade name for a product you might be familiar with, and that's Vaseline. And Vaseline, also known as petroleum jelly, is a longer molecular weight alkane or mixture of alkanes. And if you know about, ever thought about it, and I have, surviving in tough situations, a survivalist trick is, and it's better than using baby oil, Vaseline is also flammable. Not as flammable as baby, but it is. And a survival trick where you need to make fire easily, how do you have something that helps you make fire to stay warm? Well, you take some cotton balls and you rub in Vaseline because Vaseline's flammable, and you keep those in a baggie if you ever need, you're out in the wild or wherever, to make fire easily. Take one of those cotton balls impregnated with Vaseline, and it will catch fire very easily. Now, if you go to even longer chain lengths, we have what's called paraffin wax. And paraffin wax is very long chain lengths of hydrocarbons. And it's a solid. And where do you find paraffin wax? Candles. And 50% of the weight of a candle is paraffin wax. In fact, I'll teach you later on what's the other 50%, because I worked for a company that got their start in about the late 1700s, yeah, that long ago, making molecules, and they made candles. This was a company since been bought out by someone else called Unichem Chemicals, that was at that time part of Unilever, and they were headquarters in the Netherlands, which I went to a lot of places. At my level, being a senior research and development manager, I would go to Europe a lot of times during the year, usually 4 or 5 times, and I'd stay there anywhere from 2 to 4 weeks, yeah. And when I worked for Unichem, I would stay in The Hague, and I'd go to a city where their headquarters was. It was about a 20-minute train ride. The trains in the Netherlands are fantastic, the interurban trains. And the name of that city was this. Now, Americans know that as Gouda cheese, and that city and area is famous for their cheese. But the Dutch pronounce a G as a hard CH, not like Americans. Now, because I know Hebrew and I can pronounce a hard CH, Gouda in the Netherlands is not pronounced Gouda, it's Gouda. And I worked in Gouda, and I'd get off the train in Gouda. I have about a 10-minute walk by a canal, by a windmill. It was just a beautiful way to start your morning. All right, now, why am I showing you this? Because on a test, I could ask, give an example of an alkane in your daily life. And what could you do? You could put down methane, propane, gasoline, baby oil, Vaseline, or paraffin wax. So these are all products that contain alkanes that you use. Now, it's time for me to give a special homework assignment. Yep. And that is, while you're out and about next couple of days, when you drive by a gas station, think about they're selling alkanes, and they are. And remember, when you're not in my class, organic chemistry is all around you. I stole that from SpongeBob. It's all around you, and it won't hurt for you to think about it. Trust me, I'm a PhD chemist. I'm a doctor at work, but really think about it. It's all around you, organic chemistry. All right, guess what? We have finished. Thank you, Jimmy. But anyways, we have finished the alkane chapter. And what that means is tomorrow, summer, we're going at a faster rate. Tomorrow, I'll go through the alkane problem set. And I highly, highly recommend you try some of, you don't have to do all of them, but try some of the problems before I do. And that will help you do good on test number 1, which is coming up in a week or two, week and a half. And you don't want to fall behind. And I'll give you a pro tip. You're not going to learn organic chemistry the night before a test. I always studied hard throughout, and I didn't wait until the day or two before a test to learn organic chemistry, because you're not going to do it. Even I couldn't pull it off when I was an undergrad, because I knew I couldn't and I didn't. So tomorrow I'll do the problem set. And with that, we're done with the first full chapter. And you know what that means? It means new functional group, new chapter. And let me close this. Let me get to the new chapter. And that new chapter is Alkenes and Alkynes. Ooh. Now, hydrocarbons are not really considered truly a functional group, even though you talk about them separately, like I just said. But now, Dr. White's happy. Oh, am I happy? Because we're going to talk about real functional groups. And the first ones are alkenes and alkynes. So what's an alkene? Alkene is a hydrocarbon. Remember, that means a molecule with only carbons and hydrogen atoms that contains a carbon-carbon double bond. And we show a double bond by two lines between two carbons. So an alkene, and the alkenes are molecules with double bonds, at least one. Now, this I'll never ask on a test, but I have said, I've been told certain entrance exam ask the stupid question, if you got an alkene with 5 carbons, how many hydrogens? Will you use that formula? I will never ask that on a test or the final. And you've got my word on it, and you can see it in the video. By the way, if you notice, I've been posting them very quickly today, sometime this evening. Today's lecture will be in YouTube. By the way, thank you for making me a YouTube star. But what you should know is an alkene is a carbon-carbon double bond, a hydrocarbon with a carbon-carbon double bond, one or more. Now, what's an alkyne, Y-N-E ending? And that's a hydrocarbon molecule with only carbon hydrogen atoms that has a carbon-carbon triple bond. And a triple bond is shown by 3 lines between 2 carbons. And that's a triple bond, and we call that an alkyne. Now, once again, a formula which I'll never ask you to learn or use in my class or my test or final, but some people ask, do you have an alkyne with 7 carbons, how many hydrogens? Well, the formula is CnH2n-2, and that's why I'm talking about it. So we have a double bond, alkene, triple bond, alkyne. Now that we're getting into functional groups, the good stuff, it's time for you to start thinking about the following question. And throughout the rest of the semester, you should be thinking or asking me, and I'll be answering this, why am I learning this stuff? Well, the obvious answer is you want to do good on my test to get a good grade in Chem 170, because someone said you had to take Chem 170 or organic chemistry one semester to get into a program like nursing school or into another program or school. But why are we learning this? Well, let's think about double bonds in our daily life. Where do we find them? The produce section of the supermarket. What? Double bonds there? Yes. How many of you have ever seen a carrot? I didn't say eat it, just seen one. I assume all of you. And you know what color a carrot is? I don't think I have any in the house right now. I got to buy some. I ran out the other day. But anyways, it's orange. And why is the carrot orange? Well, let's find out. Because it contains a molecule, and this is not the IUPAC name, it's a common name, beta-carotene. Everybody see beta-carotene on your screen right now? The Wikipedia. Speaking about Wikipedia, I should mention, for many years now, Wikipedia has been heavily policed by organic chemists and chemists in general, like me. Yes, I have the credentials. When I request a change in a Wikipedia entry, it gets changed. But for a number of years now, because it is so heavily policed, I have not seen a mistake, anything dealing with organic chemistry. And I would bet also regular chemistry, but I look at organic. About other stuff, don't know, but anyways, here's the structure of beta-carotene. Now, this is the line structure, which I stay away from other than rings. And every bend in the line is a carbon, every end in the line is a carbon. And you see right here, double bond, another one, another one, another one, lots of them. And this molecule absorbs light, not all the light, but all the colors except the ones that come together that give you an orange color. And this is the molecule that makes carrots orange. It's an alkene, double bonds, lots of them. Now, how many of you heard carrots are good for your vision or eyesight? Just ask Bugs Bunny. You know, what's up, Doc? Sorry. It's going to be a weird humor Wednesday. But anyways, I'll teach you later on. Your body has the ability to react beta-carotene, break it essentially, and make a new molecule that has the common name retinal. And retinal is good for what part of your eye? The retina. And that's why it helps your vision. Now, at this point, I'm way beyond my knowledge of the human body, which is minimal at best. Oh, one thing I should teach you, a little personal lesson. And this is something a lot of people, especially at my level, forget, and other people forget about people at my level, meaning someone with a PhD and a lot of knowledge in a certain area. Because I'm an expert in certain parts of organic chemistry, doesn't make me an expert in things outside of that area. Yes, I know how to logically think. I've been trained that, but that doesn't mean I am. So remember that. But I'll stick to stuff I know. All right, let's look at another molecule while we're in the produce section. And that's lycopene. And lycopene has this structure. It's similar to beta-carotene, but it doesn't have the 6-membered rings at the end. But notice there's a double bond here, 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 lots of them. This is an alkene. And what does lycopene do? It's responsible for the red color of tomatoes. And so the next time you're in a supermarket with friends, neighbors, or loved ones, and you're in the produce section, you can pick up a tomato and say, no, that's red because of lycopene. Or you can pick up a carrot and say, you know, that's orange because of beta-carotene. People don't like hearing organic chemistry in the produce section of a supermarket, but now you know. Now let's do one more. Where are alkenes, double bonds in your daily life? And the last molecule I want to talk about is this one, and has the common name, and I'll talk more about what are common names this semester, called limonene. And if you notice, here I have a double bond, and down here I have a double bond. Now this dashed line shows stereochemistry, which I'll talk about later in the semester. So there are 2 double bonds in limonene. And limonene is the molecule responsible for the citrus smell and flavor in many citrus fruits, especially like lemon. How many of you ever seen on TV or you bought your at the supermarket, buy this new cleaning product? It has that lemony fresh smell. And you think, wow. And what do? They put limonene in there to give that. Also, it does help clean things too. It is a proven cleaner. But a main reason is you've been conditioned by advertising, oh, it's got that lemony fresh smell. It must be a great cleaner. And some of them are, some of them, well, you'll find out maybe they aren't. So those are all examples of alkenes, carbon-carbon double bonds in your daily life. Bet you didn't think I'd get into carrots and tomatoes in this class. All right. So we have alkene, double bond, alkyne, triple bond. Now switches off for this slide, click, but just some observation. Hydrocarbons that contain less hydrogen atoms than alkanes are called unsaturated hydrocarbons. That means they have either a double bond or triple bond. Now, why are we calling this unsaturated? Because you can put hydrogen in. I'll teach you this chapter that if you react hydrogen gas, H2, with an alkene or alkyne, you'll make a carbon-carbon single bond, an alkene. In other words, it's unsaturated because you can put in more hydrogens. Everybody see me now? Hold on. You can put in more hydrogens. This is going to look like it's coming right out at you. But anyways, that's why. And the alkanes are saturated because you can't put any more in. We're stuffed, we're full. And that's how they came up with those names, I think. It would make sense. All right. Let me put it up on the screen. Pull the slide. I forgot to. Alkadienes die to ENE double bonds. All right, let's talk about nomenclature. And nomenclature, remember, is the fancy word for how to name stuff. And I'm going through the IUPAC nomenclature because that's the only nomenclature there is in chemistry. And a double bond, the ENE ending is used to designate that a carbon-carbon double bond is present. Now, this part here I should have taken out. When more than one double bond is a diene, 3 is triene, ignore that. Now, for a triple bond, you have the ending YNE. And this is used to designate a carbon-carbon triple bond. In a couple of seconds, I'll show you what do I mean by the ending. And again, I apologize, Dr. White was lazy. Should have taken this out years ago. I don't, but I'm lazy. Organic chemists can be very lazy. For two triple bonds, die meaning 2. All right, now let's look at, I got a question. The answer is, Nana, and I hope I'm pronouncing your name correctly. If not, correct me. Are you talking about for unsaturation? When you say definitions, this slides out. I mean, on this slide, this material will be on test. All right, this you won't have to know. That's why I said click, the switch is in the off position. But nomenclature, this you don't have to know. But nomenclature, and I'll teach you about the ENE and YNE ending, but you should. And Jimmy, the answer is yes. I call it the review, and I have to redo it because it's in cursive. So that's one of my weekend projects, to redo it because it's in cursive. All my reviews, if you go to the lecture section, you'll see I have a review for tests 1, 2, 3, and 4, and then all combined are what you use for the final. So Jimmy, does that answer your question? Both of you, thank you. Remember, there's no such thing as a dumb question. No such thing as a dumb question in my class. All questions are good. And not only do you know the answer, you probably helped a couple other people in the class who are wondering the same thing. All right, now let's talk about nomenclature of alkenes. So I better draw an alkene on the whiteboard. Now, from now on, there are a couple important things you should always remember and do. One, how many bonds to carbon? 4. Next, when you look at an organic molecule, look for what's different. What's not a carbon-carbon single bond or carbon or hydrogen atom should get your attention like that. Why? Because that's where the fun is and all the action happens. And if we look at this molecule, oh, look, a double bond. Now, another thing about a double bond, that counts as 2 bonds to carbon. So if we look at this carbon right here, has 1 bond here, a double bond there, that's 3. There's always 4 bonds to carbon, 4 minus 3 equal 1 hydrogen. If we look at this carbon right here, it has 2 bonds, and there's always 4 bonds. 4 minus 2 is 2, and that's why it has 2 hydrogens. Now, how do you name this? Count the number of carbons in the longest chain, and there's only 1 chain here in this example that has both carbons of the double bond. 1, 2, 3. And look up, and hopefully you've started memorizing, since I'm going through chapter alkanes or hydrocarbon problem set tomorrow, you'll need, you need to know this chart, hint, and 3 carbons propane. Well, wrong one, right one. Wait a second. All right. So it's propane, but the ane ending, propane, you drop, and it's a double bond. So you add ene ending, propene. Again, ane ending at the end of the alkane is dropped and it's changed to ene ending. And that's why I said earlier, the ene ending tells you, this tells you there's a double bond. Now, next, you have to tell which carbon has the double bond, the lead carbon that's closest to the end of the chain. And you number it from that side. So here, this is 1. If I went the other way, it'd be 1, 2. Whichever one of those is smaller, this is 1 propene. And that's how you do a double bond. Let's do another one. All right, let's take a look at that molecule. It's your turn to find out, do you see something different? Something that's not a carbon-carbon single bond or carbon or hydrogen atom? Time's up. And the answer is yes, there's a double bond. And how do you name that? You find the longest chain with both carbons of the double bond. So I can say 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, if I go this way. And which is the longest chain? Hopefully I'll pick 6. Remember, the math in this class is really tough. So the longest chain with both carbons double bond is 6. And you look at the alkane name for that. And hopefully ASAP, as soon as possible, like now, you've learned this table. 6 carbons, hexane. But we have a double bond, so you drop the ane ending and replace it with ene. So hexane, drop the ane, put in ene. Now, where is the double bond? You look at the carbon that's closest to the end of the chain and give that the lowest number. In this case, it's this carbon, and the lowest number is 1. 1 hexane. Next, are we done? No, as soon as we say one hexene. We've spoken for that, but oh, look, it's an alkyl group. And CH3 is your old friend by now, the methyl group. And again, if you forgot, which I hope you didn't, you need to learn this table as soon as possible. And CH3 is called the methyl group, 2 carbons ethyl, 3 carbons. If it's bonded to the N carbon, it's then propyl. If it's bonded to the center carbon, it's isopropyl. Now, 4 carbons to the N carbon is N-butyl. 4 carbons, 3 to center to the chain or whatever ring is tert-butyl. And later on, like next week, I'll just get lazy and call it T-butyl, which is what most organic chemists, like everybody, calls it. So we have a methyl group. And now we have to say what carbon is it on. But remember, we named this as 1. Therefore, this is 2, 3, and it's on carbon 4. So it's 4-methyl, 1-hexene. The ENE ending tells you have a carbon-carbon double bond. And that's how you do it. How are we doing time-wise? Here's one for you to try. Give the IUPAC name for that molecule. Go. Go. That wasn't polite. I'm sorry. Not really. And for those of you who haven't learned, here's this table. Look up 5. Remember, on a test, you're not allowed to use that table. You have to learn it. All right, my turn. We're running out of time before the break, so I'm going to push ahead. What do we see that's different? Look at a molecule. Look for what's not a carbon-carbon single. Ooh, a double bond, or we'll learn later on carbon or hydrogen atom. So I have a alkene, a double bond. How many carbons in the longest chain? There's only 1. 1, 2, 3, 4, 5. 5-carbon alkane is pentane. Drop the ANE ending. Remember, drop the ANE ending and replace it with ENE. And where's the double bond? The carbon closest to the end is on carbon 1. So that's 1 pentene. And if I look at the clock, it's time for a break. So with that, come back in 5 minutes at 2:55, and we'll continue. Time to get going, or I could have done this one. Time to get going. All right. Before we get back to what we're organic chemistry, quick thing tonight on Monday and Wednesdays, and today, let me check. Yep, it's Wednesday. My computer says so. I'll have my office hour tonight from 6 to 7 on Zoom. Now, let me just tell you that a lot of times I'll have just the hello sign says at the bottom, say something, get my attention, because I'll be on another computer or doing something else in my office, and that will happen. Sometimes if I'm on this computer, yes, I have a couple of computers in my office that I use. If I'm on the internet, you'll just see somebody on the internet doing something. If when you log in and you see a picture up here, whether it's a sign or someone on the internet, it's me. Say something, my speaker's up here, I'll hear you and know to get to work. All right. Let's continue on. Now, while we're talking about double bonds, remember double bond is an alkene. ENE ending tells you double bond, 2 lines between there. Let's talk about cycloalkenes. You can have a double bond in a ring. How do I know it's a double bond? To 2 lines between the 2 carbons. Remember, every bend in a line is a carbon. How do you do? And I don't have it on the sheet because I should someday, but I didn't today. So let me do it the old-fashioned way on the whiteboard. You name this as a cycloalkane. How many carbons in the ring? 1, 2, 3, 4, 5. And that would be pentane. And it's a ring cyclopentane. But remember, for a double bond, you drop the ANE ending at the name of the alkane, or now cycloalkane, and you replace it with ENE. So that's that. Now, in a ring, when that's the only functional group, and in this class that will be true in real life. No, and now UPAC has rules for the when it's more than one functional group, which I won't teach in this class, but I do know. One of the carbons of the double bond is always carbon 1, and 1 is always carbon 2. And because of that, you need no number. So I'm done. Let's look at this molecule. Now, here's where it gets interesting, but I have faith in you, and you can handle it. And if you don't, ask questions, because there's no such thing as a dumb question. Question is 3 points each, give the IUPAC name for this molecule. So how do you do this? You look for what's different. Ooh, I've got a ring, but what's not a carbon-carbon single bond? Ooh, a double bond. So this is a cycloalkene. How many carbons in the ring? 1, 2, 3, 4, 5, 6. This is not in a ring and you don't count it. That's cyclohexane. Remember, for rings, we use the prefix cyclo. Remember, for a double bond, ANE at the end of the cyclohexane or any alkane is dropped and replaced with ENE. So it's cyclohexene. Now, here's where it gets interesting. One of these carbons of the double bond has to be carbon 1, and the other will be carbon 2. And you number it in such a way that the substituents, the methyl group here, the alkyl groups, also have the lowest numbers. Again, one of the carbons has to be 1, the other has to be 2, and you number it in such a way that the methyl group, in this case, also has the lowest number. So if I go this way, that's 1, this is 2, this is 3. Now here's a mistake students make, and I'm showing it so you don't. What if I call this 1 and they say, oh, I'm going to make this right here 2? You can't, because one of the carbons has to be 1, this has to be 2, and therefore if I continue on, so you have a choice. Do you want the methyl group 3 or 6? Alkyl groups always have the lowest number, and the answer is 3. So this is 3-methyl cyclohexene, ENE ending double bond. Your turn. What would be the IUPAC name for this molecule? And in case you forgot, look at 5. And remember, if you're having problems, ask questions. There's no such thing as a dumb question. If you have a question, I would bet that a good part of the rest of the class has the same or similar question. Oh, by the way, I should warn you, I only say I'll bet when I know I've won. So remember that. If I say I bet, that means I've already won. So never bet with Dr. White. All right, let's take a look at this. Look at a molecule, look for what's different. What's not a carbon-carbon single bond or carbon-hydrogen should get your attention like that. And ooh, a double bond right here. And it's in a ring. How many carbons in a ring? 1, 2, 3, 4, 5. What do we call a 5-carbon ring? Cyclo, remember the cyclo. 5 is pentane. But for a double bond, the ANE ending at the end of pentane is changed, dropped, and replaced with ENE. So this would be pentene, cyclopentene. And when there's only one double bond, which will always be the case in my class, in a ring, you need no number, because one of those carbons is always going to be 1. Everybody knows IUPAC rules, knows that. So why do you have to write the 1 down that everybody knows? And you don't. All right, let's do one more. And what would be the IUPAC name of this molecule? Now, if we were in class, I'd have this up on the whiteboard. I'd write it, but 6 is what? Hint. And let's look at the key alkyl groups. 3 carbons with the center carbon attached to a ring. Hint, right here, begins with an I. Again, you won't have this chart when you take the test. That's called cheating. And I'll know. So remember, one of the carbons has to be 1, one has to be 2, and you do it in such a way that the alkyl groups have the lowest numbers. And if anybody's getting a headache, take 2 aspirin, don't call me in the morning. By the way, aspirin and other painkillers, I'll teach you, is organic chemistry too. See, it's everywhere. All right, I think everybody's done, so I better get to work. All right, if you look at this molecule, you look for what's different, what's not, a carbon-carbon single bond or carbon or hydrogen atom. Ooh, a double bond. And it's in a ring. How many carbons in a ring? 1, 2, 3, 4, 5, 6. Every bend of the line is carbon. Good news, I use software for tests. I don't hand draw them. And that's cyclo, 6 carbons in a ring is hexane, cyclohexane, but I have a double bond. I drop the ANE at the end of cyclohexane and replace it with ENE. And that tells you have a double bond. And now, where's that double bond? Well, you don't have to do that, but one of the carbons has to be 1, the other has to be 2. That's one way. Did I, oh, let's see, no, 1, 2. All right, so you have a choice. This is an isopropyl group. And which is smaller number, 4 or 5? And the answer is 4, because this is carbon 1, the other carbon double bond is 2, this is 3, that has to be 4. So this would be 4 isopropyl cyclohexane. And actually in real life, this is closer together. By the way, this, and I've been an editor for journals, means it crunches it. On a test, I'm not going to take out a ruler and say, oh, you're more than 6 millimeters apart. I'm going to take off. No, if you have it on the wrong page, yeah, but not apart. All right, one of your colleagues just asked a question, why couldn't it be 3? When you number one of the carbons, the double bond always has to be 1, the other has to be 2. This is 1, this is 2. That's why this is carbon 4. Now, and this is a common mistake students have. If I call this 1, can I make that 2? Can I make that 3? Well, what about this carbon? It's going to be carbon 6, and it can't be. It has to be one of the carbons, always has to be 1, the other 2. And that's just the way IUPAC came up with their rules. And that's why you don't do that. I'm glad that makes sense. Does it make dollars too? Ooh, that was awful. Now, I have mentioned this, but one of the things that you're saying, and hopefully you're saying, is the beauty of the work IUPAC. And IUPAC, if you do a name correctly, any molecule only has one name. Any molecule only has one correct IUPAC name. And what they did was phenomenal to get that. All right, let's go back and look at alkynes. Now, an alkyne is a carbon-carbon triple bond. And the ending for an alkyne is YNE. Whoops, wrong color. And let's take a look at this molecule. And once again, I'll ask you, when you look at an organic molecule, look for what's different. What's not a carbon-carbon single bond or carbon or hydrogen atom should get your attention like that, or like this. I can be a wild and crazy guy, and I am. And what do we have here? Ooh, a triple bond. And a triple bond ending is YNE. So how do you name this? You find the longest chain with both carbons of the triple bond. 1, 2, 3, 4, 5. You name it as an alkane. 5 carbons is pentane. But now for a triple bond, remember 3 lines is a triple bond. You take the ANE ending of the alkane name, drop it, and replace it with YNE. And therefore, this becomes pentyne. And like a double bond, you find what carbon atom is closest to the end of the chain. The examples I used for double bonds was 1, but I figure I better switch. And this carbon is 2. If I start numbering from the other side, 1, 2, 3, the lead carbon here would be closest to the end 3. Here it's 2, which is a smaller number. Time's up. Hopefully I'll pick 2. So this is 2-pentyne. And if you have alkyl groups, you do it the same way as we've always done alkyl groups. And why don't you try this one? What would be the IUPAC name for this molecule? And I forgot a hydrogen. Don't look. Now you can look. Now, in case you forgot or haven't learned, which you may not have, but hint, you should learn this. The IUPAC names 7, 7. And now you see why you need to learn this, because on test 1, roughly 50 points will be nomenclature. A couple of days before test 1, I'll give you a breakdown of what the points are, how many points, how many pages, how many questions. But one thing I should mention now, so you all can relax. First of all, I forgot to tell you this. I teach by my golden rule of teaching, and that is I don't do to my students what I didn't like done to me when I was a student. And yes, I can still remember when I was a student in a galaxy far, far away. But anyways, when I write tests, and I've been doing it long enough so I know I can do this, one, every question on my test, I've covered the concept behind that question at least twice, actually, it's usually more, in lecture. Again, every question on my test, I will cover the concept behind that question at least twice. It's usually a lot more, but I guarantee at least twice, and usually, like I said, it's a lot more. Next, my tests are made that if you've studied and done the practice problems, hint, do the practice problems, you'll have, and because you got to upload and everything, it'll be overnight, but I'm going to ask on the honor system, take about an hour, hour and a half. If you, or when I do this when we're face-to-face, where the students only have 55 minutes, they don't have to scan it, they just hand it to, and if you studied and done the practice problems, my hourly exam, most students are done 35 minutes. You have plenty of time to finish. Also in Chem 170, I never have and never will give a multiple choice question. Dr. White hates multiple choice tests. They're designed to trick you, not show how much you learn or know from the material you were taught. So I thought I'd tell you that. It's coming up, but now you know. All right, let's get back to this. What's the IUPAC name for this? Look for what's different. What's not a carbon-carbon single bond or carbon or hydrogen atom should get your attention like that. Hopefully that did. And yes, I do that in a classroom too. Oh, a triple bond. And we find what's the longest chain with both carbons of the triple bond in it. And I can go 1, 2, 3, 4, 5, 6, 7. Remember, this is how I write a 7. Or I could go 4, and over here is 5. Which is larger, 7 or 5? Time's up. Hopefully you pick 7. 7 alkane is heptane, which I didn't want to write all that out. Remember, for a triple bond, find the alkane name, drop the A and E at the end, and replace it now with Y and E. And here, oops, I'm thinking double bond. That'd be heptyne. Now, which carbon of the triple bond is closest to the end of the chain? If we start here, it's on carbon 2. If we start here, it's 1, 2, 3, 4, 5. Which is smaller, 2 or 5? And time's up. Hopefully I'll pick 2. So that's 2-heptyne. And as soon as we say that, all of that is spoken for. Are we done? No. Oh, look, it's your good buddy, the methyl group. And what carbon is it on? Well, we've already defined this as 2. This has to be 3. Therefore, it's on carbon 4. So that's 4-methyl-2-heptyne. Let's go through that again. You look at the molecule and look for what's different. What's not a carbon-carbon single bond or carbon or hydrogen atom. And there's a triple bond. Water time. Boy, this alkenes and alkynes is thirsty work. And you find the longest chain with the both carbons of the triple bond. And now that's 7. You take the alkane name, heptane, drop the A and E for a triple bond, put Y and E, heptyne. Next, like a double bond, what carbon is closest to the carbon, then to the chain? And here, if we start from this side, it's on carbon 2. If we start from this side, it's on carbon 5. which was smaller? Was it 1, 2, 3, 4? Actually, it's carbon 6. I counted wrong. Bad Dr. White. But 2 is still less than 6. So that would be 2-heptine. Then we have a methyl group. If this is on carbon 2, this is carbon 4. So it's 4-methyl 2-heptine. Now, I'm going to be talking about bond angles in a little while. But what I will tell you now is, unless you get to a really, really, really large ring, you can't have a triple bond in it. You can't have a triple bond in a 6-member ring. It's impossible. And because of that, I think in all the years I've been doing organic chemistry, which is a few more than you, should I do this? Everybody see the date? That's when I got my bachelor's degree. No, it wasn't when I was born. That's when. So I've been doing this a few months more than you people, but you can't. So there, you don't have to worry about cyclohexynes. I think many, many years ago, I saw a paper where somebody was trying to press, look how good I am, look what I can make, and it had no use in the daily life or anything in industry, but they made a ring, huge ring with a triple bond. And that's the last time I've ever seen something like that. All right. How are we doing time? What? Doing good. Now, one of the things that I'll come back is we've done, here's a molecule, what's this IUPAC name? I'm going to come back, but I want to do something first. We'll also do, here's the name, draw the molecule. But we did our practice problems. We'll do some more. Let's talk about common names. In addition to IUPAC names, there are a few common names that have been around for unsaturated hydrocarbons. These existed long before IUPAC, and they still are used. Now, ethylene, and this you don't have to know, but this is the structure of ethylene, and it's used to make what's called polyethylene. I'll teach you later. You know that as saran wrap. And polypropylene or propylene is this molecule. Now, the one I do want you to know for test number 1 is the common name acetylene. And acetylene is the simplest of all alkynes triple bond, 2 carbons. And you can write this. Now, this is called a right justified hydrogen. If on the very last carbon, you can also put the hydrogen on the outside too. Left justified. My software likes to do this, and even when you override it, it still is a so both of these are the same. 3 lines in math means identical. Ooh, threw in some high-level math. Now, how many of you have ever seen in a car body shop where they have to heat up something or cut a piece of metal, they have that torch that has the real hot flame and cuts right through metal? Or if you've ever seen on a movie or TV, the burglars are trying to get into a safe, and they have this torch and they cut out the lock. And that's called an acetylene torch. And that uses acetylene, nobody calls that ethine, plus oxygen, which burns at a much higher temperature than methane, your natural gas, or propane for your barbecue. Now, when it comes to common names, I will never ask on a test, here's a molecule, what's its common name? Well, for the first part of the semester. Later on, I'll do a few, but I'll explain later on why. But for now, I won't. But I will ask on a test, here's a common name, draw the structure. And why am I doing that? Because one of the skills you'll have when you leave my class is you can pick up ingredients or something you buy, look at the ingredients label, and have an understanding of what that stuff is. And I'll teach you later on, how to find out, is that chemical that's in whatever I eat or put on my skin or my hair or ingest or whatever, is that dangerous? I'll teach you how to find that out. So you should know this one. You should know acetylene is that structure. Now, click switches off. And I didn't, hold on. Guess what I forgot to? Yep. Once in a while, even I forget to. All right, let's repeat this again. Hint, you should know the structure of acetylene. You don't need a ethylene or propylene, but you should know the structure of acetylene. All right, switches off. Another important name is a substituent, 2 carbons in a double bond attached to something. And that's called a vinyl group. And how many of you ever heard of vinyl floors or vinyl? When I was in high school, all my parents and all my friends' parents had vinyl covers, clear vinyl covers for the furniture in their living room. And if you had shorts on in the summer, you'd stick to that. Oh, it was uncomfortable as heck, but everybody had it. Vinyl means a carbon-carbon double bond attached to something. That's called an alkenyl group as opposed to an alkyl group. But you don't have to know that, but I thought I'd talk about it because it's interesting. All right, next couple of slides, click. I'm going to turn the switch. Will this be on the test in the off position? But it's also something important to help you understand something that will be on the test and something you should know in organic chemistry. And that's the pi bond. And the pi bond is abbreviated by the Greek letter pi. And it contains different types of orbitals. That's where the electrons are. Now, the bond angle is 120 degrees. And because of the way it's set up, unlike a carbon-carbon single bond, which can rotate, a double bond and a triple bond are locked in place. There's no rotation around a carbon-carbon double bond or a triple bond, which I'll talk about later. And this is due to the pi bond. Again, switches off. I'll never ask this. And here we have a carbon that's in a double bond. Remember, carbon has 4 valence electrons, and one would be in this orbital, one would be in this orbital, one this one, and this one. An orbital is an area in space that if you could stop all motion, like when electrons moving around, that's the probability in that area that's colored, like this one right here, this electron would be somewhere in there. This electron in the p orbital would be somewhere either here or here. It's moving around. And if you look at it from the top, it looks like this. Again, switches off. Now, when you're forming a carbon-carbon double bond, you have 2 carbons coming together. And the first thing is, remember, any bond is sharing of pairs of electrons. And now we get the sp orbital overlap. And this is called a sigma bond, like a single bond. And then the 2 p orbitals right here overlap and share. And here there are 2 electrons moving around all this blue area here. So a double bond has a sigma bond and a pi bond. And now I'm going to turn the switch on. Something you should know for this class. That is a carbon-carbon double bond, has 1 pi bond and 1 sigma bond. Again, you should know a carbon-carbon double bond has 1 pi bond and 1 sigma bond. And while we're here, let's look at a triple bond. And this has 2 pi bonds and 1 sigma bond. Again, this is sigma. And this is pi. No E there when you're doing Greek letters. Oh, by the way, I was in a fraternity house, Alpha Epsilon Pi, and someday when we have some time, ask me about it. The movie Animal House with Jim Belushi was written about my fraternity, actually my chapter when I was at IIT, and I was in there. I actually met Jim Belushi and Dan Aykroyd when they were at Second City. Am I famous or what? All right, so double bond, 1 pi bond, 1 sigma bond. Now, because of this overlap, they're stuck. They can't rotate like a carbon-carbon single bond. And because of that, a double bond, I'm looking where I hit something, is called, the shape of a double bond is trigonoplanar. Planar means it's flat in a plane like a piece of paper, and the angles here between the 2 hydrogens and the carbon double bond is always the same. I think that's 120 degrees, like I said earlier. And here's a model. Here's my double bond, a pi bond, sigma bond. And notice if we forget about these right here, but the carbon here and here, and the hydrogens here and here, and here and here, they're in a plane, they're flat across. And that has very important ramifications in terms of things like certain things that are healthy for you and not healthy, really. Now, did I tell you how great IUPAC was? And that 1 molecule only has 1 name and 2 different molecules never share the same name. They did a great job. Again, any molecule in organic chemistry has only 1 name and 2 different molecules never have the same, never. So let's go back and look, and now we know about stereochemistry. Let's show an example of a double bond. Now, it turns out for a triple bond, it's linear, and I'll talk more about that. Now that we know about stereochemistry, how things are arranged in space, we can talk about this molecule. Let's do 2 of them. I'll throw in an extra one, no extra charge. And now I'm showing the bond angles. And I promised I'd do a second one. Let's call this A, let's call this B. Now, how would you name A? Well, you find the longest chain. Even though this is bent up, this carbon is bonded to this carbon, to this, 4 carbons. That's butane. It's a double bond. So drop the A-N-E ending, put in E-N-E-N, and that's butane. If I start here, 1, 2, I could also start here, 1, 2. This carbon or this one, the closest to the end of the chain, is 2. So this A is 2-butene. All right, let's do B. How many carbons in the longest chain? 1. It's bonded to this one, 2, 3. Even though we have a bend, remember chains can bend. I'm showing the 120 bond angle here, 4. So that's butane, but a double bond. We have butane. Now, remember I told you, or IUPAC, they've never had a case where 2 different molecules have the same name. Doesn't happen. But anyways, let's continue on with this. What carbon is closest to the end of the chain of the double bond, here or here? We can call this 1, this 2, or this 1, this 2. So, 2-butane. A and B are different molecules. They can't have the same name. Relax, take a deep breath. IUPAC thought of this. And let's go through what's called cis-trans isomerism. And that means isomers, molecules with the same number of atoms and the same type, but they're put together different. Now, by the way, switch is on. Due to no, I'll never ask this, but due to no rotation, here, a double bond. Let me steal from my ring here. Single bond, I can rotate carbon-carbons all the time. Double bonds, nope, you're not going to rotate unless you snap the model, and I'm not going to, because that would break the double bond. It's locked. And notice I have the bond angle, just like I drew hydrogen up, methyl group down, methyl up, hydrogen down. So there's no rotation around the carbon-carbon double bond. And because of that, to handle the situation we talked about, IUPAC came up with the following. The prefix cis means same side for 2 of the same groups or atoms on a carbon-carbon double bond. Trans means opposite. That means 2 groups or 2 atoms that are on the opposite side are called trans. So these are the prefixes for alkenes, double bonds, nomenclature. So let's go back to our problem here. Now, if we look at this, and if I had a plane right here, like a piece of paper coming right out, notice the hydrogens or these CH3 groups are on the same side. So now the name for A, same side cis, this is called cis-2-butene. Now, if we look at B, and again, that plane right here, notice the hydrogens are on opposite sides of this plane. And same thing with the CH3 groups. And when it's opposite, even says on the screen here, oh, that was awful, sorry. Opposite is trans. So this is now trans to butane. Now, when you have 2 of the same group or atom on the same carbon of the double bond, you can't have sister trans isomerism, and therefore you don't use that. And the example is, if you notice, go back and look at the examples I did. It was always on carbon 1. Why? If we look at this molecule, I have a double bond. How many carbons are there? 1, 2, 3, 4. That's butene. Here, this is the close to the end, so it's 1 butane. Do you put cis or trans? No, because I have 2 hydrogens on the same carbon, or it could have been 2 other types of groups, but for this class, I'm going to skip the hydrogens, because look, here's this hydrogen, it's on the same side of the plane as this one, but it's on the opposite. You can't have both at the same time, so you have neither. Again, cis, when 2 of the same atom or group, and for this class, it'll be hydrogens, are on the same side, and if they're opposite, it's trans. And if we look at this molecule, what would be the IUPAC name? And after the break, I'm going to let you have some fun doing this too, because I share the fun. Dr. White won't hog it all to myself. And what do we see that's different? Remember, when you look at an organic molecule, you should look for what's different. What's not a carbon-carbon single bond or carbon or hydrogen atom should get your attention like that. Let me do it again, like that. And double bond. How many carbons in the longest chain with the double bond? 1, 2, 3, 4, 5, 6. Name that as an alkane, hexane. Double bond, drop the ANE, put ENE. Which carbon is closest to the end? Here it's on carbon 2. Here, if I start here, 1, 2, 3, 4. So which is smaller, 2 or 4? It's carbon 2. And now, because I'm showing stereochemistry, notice these hydrogens are on the same side of this dotted line of plane, cis, same, trans, are opposite. Well, these are on the same side. So this would be cis 2 hexene double bond ENEND. All right, any questions so far? And now a commercial from Dr. White. One, don't forget, my office hour is tonight. If you need help, it's on Zoom, so you don't have to get in the car and go to ECC. I won't be there, and you don't have to go there. And 2, don't forget your homework assignment. Remember that when you're out and about today or tomorrow, and you drive by a gas station, remember and think about, they're selling half the weight of gasoline are alkanes. Or if you happen to be cooking later today or tonight, or somebody else is cooking for you, and it's on a natural gas stove or an oven, they're using alkanes, methane. Or if you happen to wash your hands and you're using hot water along with the cold water, so it's comfortable, that hot water is heated up with methane, which is then alkane. And if you're using Vaseline, say on your skin, back when I was in high school, some guys would put it in their hair. They were called greasers, but that's another story, another day. But anyways, the Vaseline is an alkane. And if you look at a candle, half the weight of the candle is an alkane. So remember, organic chemistry is all around you. I stole that from SpongeBob. And that's one where he teaches Squidward about imagination. Yes, I still like my cartoons. But anyways, it's all around you and it won't hurt for you to think about it. And with that, I'm going to give you a whole extra 60 seconds on our break. Come back at 3:50 and we will continue. I'm going to get up and stretch. Time to get started again. All right, quick reminder. Don't forget tonight from 6 to 7, I have my office hour on Zoom. And don't forget tomorrow, lab number 1 is due. If you don't have a printer for lab number 1, you have to put down on a piece of paper, write down the identity of the unknown, and then answer the questions. When you answer the questions, if you don't have a printer, you don't have to write out the questions, just put down your answers. And good news, I can read cursive or printing too. All right, we were talking about, and let me put this up on the screen, nomenclature of double bonds using cis and trans. So let me give you a chance and the question is, what's the IUPAC name for that molecule? 3 points each. Your turn. First, you have to find out how many carbons are in the longest chain with both carbons of the double bond. Name it as an alkane. Drop the ane ending, ene, and I'll let you figure out the rest. Now, hopefully by now you found out there are 8 carbons in the longest chain. And in case you haven't memorized this hint, this should help you. 8 carbons. One of these days, I'm going to play some game show music like dun, dun, dun. You know, they play on TV while they're waiting for the contestants to write down their answers. Nah, I won't do that. All right, I think it's time for me to get to work. So when you look at an organic molecule, what do? You look for what's different. Well, it's not a carbon-carbon single bond, carbon or hydrogen, and here we have a double bond. How many carbons in the longest chain with double bond? 1, 2, 3, 4, 5, 6, 7, 8. And it's a double bond. So you name it as an alkane, octane. Drop the ane ending, put ene, octene. And then what carbon is closest to the end? We start here, it's carbon 3. We start here, it's 1, 2, 3, 4, 5. Which is smaller, 3 or 5? Time's up, 3. And now, since I've shown stereochemistry, and sister trans is needed. And there's the plane. And if we look at the two hydrogens, are they on the same side or opposite sides? And the answer is opposite. One is above, one is below that dotted line. And for opposite, we use trans. So this would be trans 2-octane. And let's do one more, and that would be this molecule. Question is, what's the IUPAC name for that molecule? And first you have to find the longest chain with both carbons of the double bond. And since some of you may not have learned the table of number of carbons, the IUPAC names, hopefully you will by tomorrow, or at least at the latest by Monday. Remember, tomorrow I'll go through the chapter on alkanes problem set. But to help you out, 6. Hence 6. And I think by now everybody knows what a CH3 group is. It's your good friend. All right, let's say, well, nice. Hold on, Dr. White. Okay. Okay, let's get to work. Now, how do you name this? You look for what's different. What's not a carbon-carbon single bond or carbon hydrogen? Ooh, look, a double bond. And how many carbons are in the longest chain with both carbons of the double bond? 1, 2, 3, 4, 5, 6, 5, 6. So either way, it's 6 carbons. Hexane. Double bond, drop the ane ending, put ene, hexene. And what one of the carbons, which is the closest to the end of the chain. And notice this carbon right here, 2. I start the other way, 1, 2, 3, 4. So which is smaller, 2 or 4? Hopefully I'll pick 2. Now, notice I have the same atom on each carbon double bond, hydrogen. Did I tell you the closer we get to the 4th of July, the worse my hydrogens look? Not really. But anyways, sounded good. The hydrogens are on the same side. Remember, cis, same side, trans, opposite side. So they're the same. Both are underneath the line. So this is cis 2-hexene. But wait, we're not done. As soon as you say that, that's all spoken for. Oh, we've got something left over, an alkyl group. And it's your good friend, the methyl group. And what carbon is it on? Well, we've already defined this as 2. That's 3. That's 4. It's on carbon 5. So it's 5-methyl cis 2-hexene. Again, find the longest chain with both carbons of the double bond. Next, name it as an alkane. Double bond, drop the A on the end, put E on E. Next, what carbon of the double bond is closest to the chain, end of the chain? And that's this one carbon too. And then since you have a hydrogen on each carbon of the double bond, and it's below the line or the plane, that's cis. And finally, on carbon 5, we have your good friend now, the methyl group. All right, in a second, I'll be going through, here's the name, how to draw the structure. Now, one thing you didn't realize, but I didn't tell you, is when you have a double bond in any ring, this is always cis. Since everybody knows it's always cis, as small rings like that, we don't put it in. Now, the following, you do not have to write this down. Does everybody know what that is? It's transparent. These are trans, opposite sides, pair, and. Did I have an emoji that goes boo? Now, when you say cis comes first, you mean here at the very beginning? And the answer is, I don't know if they have exact rules. I bet they do, but the cis always goes in front of the number 4 or before, or I should say, you start out with the substituents, then cis, the number, then that at the end. So you wouldn't put cis all the way out in front of the 5. It's just not the way it's done. Does that answer your question? All right. Now, there are 2 types of nomenclature questions. And the second one is, draw the structure. So let's do some. And I'll do one that, I'm going to share because it's fun. I want you to have fun too. And the question is, draw cis-2 heptene. How do you do this? You always start from the right and move left. EN ending tells you double bond. If that were ANE, heptane, 7 carbons. Where does the double bond start? Carbon 2, and notice it's cis. So I have 1 carbon, then my second carbon is the double bond, and I'm showing stereochemistry, and the hydrogens are on the same side because cis is same. And then 1, 2, 3, 4, 5, 6, 7. And remember, there's always 4 bonds to carbon. And there you go. 7 carbons. 1, 2, 3, 4, 5, 6, 7. The double bond starts at carbon 2, and the hydrogens are on the same side. And here's one for you to try. Trans-3-nonene. Now, in case you don't know the alkanes table, hint, you should. Notice nonane, hint. And don't forget, tomorrow will be another lab. It's already posted in D2L for you to download at your leisure. And I'll go through it tomorrow at the end of the class. And that will be due next Tuesday. Remember, summer, we're moving at a good clip, so don't fall behind. Keep up. And by the way, all of you who've been asking questions, thank you. Remember, all questions are good questions. All right, I think everybody's done, so my turn. How do you know how to draw this? Or how do you know what the secret code is to know what to draw? You start from the right, move left. ENE ending, double bond. If that were ANE, nonane, 9 carbons. Where does the double bond start? Carbon 3. 1, 2, 3. Double bond. Now, notice it's trans. Trans means opposite, like in transparent. And then 4, and I need 5 more because nonane is 9 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9. And I know there are 4 bonds to carbon, so I can figure out the hydrogens. And remember, it's your solemn responsibility to check that I'm not making a mistake. And if I do, let me know so I can correct it. And that's how you do it. Oh, let's do one more of these. Again, ENE ending, double bond, ANE, nonane, 9 carbons. Where's double bond start? Carbon 3. 1, 2, 3. It's trans, so the hydrogens are on opposite side. And why don't you try this one? 5. Ooh, I forgot something. Oops. 5-methyl. Did I tell you I was always first one down in spelling bee? Probably still would be. Anyways, 5-methyl cis 2-octane. And you're supposed to draw it. And in case you forgot or haven't learned, octane is 8. And don't forget, if you drive by a gas station, half the weight of gasoline is alkanes, mainly isomers of octane. All right, let's do this. How do you decode this? Know what to draw? You start from the right, move left. ENE ending, double bond. If that were ANE, octane, 8 carbons. So I have 1 carbon, double bond starts at carbon 2. Remember, the bond angle is 120 degrees. That's why I'm showing this. And notice it's cis. Cis means same side. Trans means opposite side. And we're talking about two of the same group or atoms, one on each carbon of the double bond. Well, in this case, cis for this molecule means hydrogen. And in this class, I'll stick to that. That's my little gift for you. And that's 1, 2, 3, 4, 5, 6, 7, 8. 8 because octane is 8. So, and notice 1, 2. But are we done? Oh no, as we go this way, it's your old friend, the methyl group CH3. And where is it? It's on carbon 5. 3, 4, 5. And now I know there are 4 bonds to carbon, so I can put in my hydrogens. And that's how you do it. All right, let's do some triple bonds. And I'll do this one. And the answer or question would be, draw the structure for the following molecule. How do you do that? Well, you start from the right and move left. And a YNE ending is a triple bond. YNE ending, triple bond. If that were ANE, nonane, 9 carbons. So I better get to work. Now you can't have cis or trans in a triple bond because the bond angle of a triple bond is 180 degrees. It's straight, like a pencil or my finger right now, if it's straight. Now, where's the triple bond? Starting at carbon 3. You can number from either side. Most of you are going to go this way. So there's my triple bond. Oh, it's your old friend, the methyl group, and that's on carbon 2. And now I know there are 4 bonds to carbon, so I can start putting in my hydrogens. And that's how you do it. Again, start from the right, move left. YNE ending tells you triple bond. And where does that ANE, if that was ANE, nonane, 9 carbons. And where does the triple bond start? Carbon 3. And then on carbon 2, there's your old friend, the methyl group. And now here's one for you to try. And why don't you draw the structure for 4-methyl 1-octyne? In case you forgot, octane has 8 carbons. Octane has 8 carbons. And there you go. Your turn. Oh no. While you're doing that, I have to get another bottle of water or I'll be thirsty. I'm back and I'm all set. All right. Question is, how do you decode this? And well, let me ask if everybody's done. I shouldn't be rude. Well, it looks like everybody's done who wants to vote. So I'm gonna get going. So how do you decode this? You start, whoops, don't do that. You start from the right and move left. Y on the ending, triple bond. If this were A and E octane, 8 carbons. And where does the triple bond start? Carbon number 1. And then if this is 1, that's 2, that's 3, that's 4. Oh, it's your old friend, the methyl group. And now I know there are 4 bonds to carbon. You can put the hydrogen here, or you could have put it on the outside. This one doesn't have a hydrogen. And that's how you do it. And that's how you do nomenclature. Oh, sorry about this, but again, I'm soon going to be putting new memory in. Let me try something first. No. All right, sorry about that. Finally, we're going to get to talk about some exciting reactions. And that's the fun part of organic chemistry, but I'm biased because I'm a synthetic organic chemist. That's what I got my PhD in from Michigan State. And synthetic is just a fancy word meaning to make. And my training and what I did for many decades in the chemical industry was make new molecules that solve problems. I'll talk later. Some of I've done are been used as fabric softeners, antimicrobial molecules, also some molecules that hold sand together to make molds to make your car engines. I've done all that. Actually got patents in those areas. But now it's time for our really, combustion, very important, but as a synthetic organic chemist, boring, but now some fun stuff. All right. Let's talk about reactions of double bonds, alkenes, and switches on. Now, alkenes can undergo what's called an addition reaction. Now, when we have a double bond, you should know there's one sigma bond and one pi bond. And pi bonds, you can break like that. Sigma bonds, you don't break. Pi bonds, you can break like that. Sigma bonds, you don't break. So the first reaction, and this is a way of showing a double bond. In math, know how you have X and Y. And if I had X plus Y equal 100, well, if X is 10, Y is 90. If X is 50, Y is 50. They're numbers. Well, in organic chemistry, we use the letter R because it's not a chemical symbol of the elements, to say something that just has carbon and hydrogen, just like X and Y in math. So what this is really saying is, if I have a double bond and I react it with something in the form AB, I'll break the pi bond, and each carbon of the double bond will get something like A and the other one B. The sigma bond, single bond, you don't break. Now, let's get into the good stuff now. And again, in this class, carbon-carbon single bonds are almost never broken other than combustion and a reaction I don't teach anymore called ozonolysis. O3 is ozone, which I've worked with. All right. Our first reaction, really good one, and that's called hydrogenation. I will never ask on a test, what's the name of a reaction? But since I know them and I will use them, I'll use them. All right, hydrogenation is the addition of hydrogen gas or hydrogen to a double bond alkene. Now, in order to make it go in a reasonable amount of time, remember, time is money. You want something done in a couple hours, or do you want a reaction you'll have to wait a couple of months, couple hours, and you use a catalyst, platinum, palladium, or nickel. And I have it here, but the better way to think of it is any molecule with a double bond, you react it with hydrogen and a catalyst, and the catalyst can be, and this you should know, platinum, palladium, or nickel. And you break the pi bond, and each carbon of the double bond gets a hydrogen. Now, one thing I should point out, this is one way to write a reaction. A plus B equal, go make C. Organic chemists are lazy, or shorthand. We can also write it this way, or put the B or other stuff below the arrow. So anytime I have a double bond reacting with hydrogen gas, that's H2, and have a catalyst, which makes it go quicker. Catalysts are not consumed in a reaction. They just make it go quicker. You break the pi bond. You should know double bond, one pi bond, one sigma bond, and each carbon gets a hydrogen. And now let's have some fun. Now, on my test, I'm going to be also doing this type of question. A lot of times, because did I tell you organic chemists are very biased? Things that are inorganic, unless you're doing work in a plant and have to worry about byproducts or waste, you're just interested in organic products. And so let's do one. And the question would be, give the organic product or products are the following, 3 points each. Well, what do? Well, you look at a molecule and say, what's different? What's not a carbon-carbon single bond or a carbon or hydrogen atom? Ooh, a double bond. And as soon as I see that, the only thing I see in that molecule right now is a double bond. Everything else, carbon, hydrogen, carbon-carbon single bonds, come along for the ride. Double bond, what am I reacting with? Hydrogen. What's this? It's a catalyst. Remember, catalyst for this reaction can be platinum, which we're using, palladium, or nickel. And what happens? You break the pi bond, and remember, this has one pi bond and one sigma bond. Pi bonds I can break like this. Sigma bond, no, you don't break those, except for combustion. We're not burning this. And each carbon of the double bond, these two, get a hydrogen, H2, H2. Now, do you break carbon-carbon single bonds? No. So I start out right here with 3 carbons. I better end up with 3 carbons. Notice I broke the pi bond. Instead of 2 lines, there's 1 line. And here are my 2 carbons of the double bond, like these 2 carbons. And each one gets a hydrogen. And now I know there are 4 bonds to carbon. I can put in the rest of the hydrogens. Now, You can write it just like this, and it's fine on a test. I tell you, I'm this close to the person who grades the test, me. And you could have also said this carbon has a hydrogen here and here. I can write it like this. This carbon has 2 + 1. I can write it like this. Either one is acceptable. The top one is just easier for you, and it works for me. So what did I do? I looked at a molecule. I looked for what's different, double bond. I look at what I'm reacting it with, double bond, hydrogen, and catalyst. I've learned this general reaction. Can't know this. And I've learned double bond hydrogen and catalyst, where the catalyst can be platinum, palladium, or nickel. I break the pi bond. One carbon gets H, the other gets H. And I have 3 carbons here. I end up with 3. I broke the pi bond. And each of those 2 carbons, the double bond, get a hydrogen. And that's hydrogenation. Now, something about Dr. White in my past, I worked for 2 companies that did hydrogenations. I actually came up with a new reaction using hydrogen to make molecules people didn't know how to make. And also part of my job was something I invented. I would be the one supervising in a chemical plant the first, second, and third times they ran it. That way I know they did it right and didn't mess up. And that made my reputation good because my stuff worked. And I've done hydrogenations on molecules or amounts up to 40, 60,000 pounds. Quick thing, tank wagon, the vehicle that brings gasoline to a gas station or milk to places, as standardized, that's 40,000. Done one reaction with a whole one of those. It's fun. But anyways, if I look at the clock, oh no, we're just about out of time. All right, remember, the melting point lab is due tomorrow by 4 p.m. Try and get it in. And if you're an hour or two late, that's okay, but don't forget to hand in a lab or you'll lose 11 points. That's going to hurt your grade. Don't forget tonight, I will be having my office hour 6 to 7 on my Zoom channel. Later this evening, I will post the video of today so you can watch it again if you want, or those of you who are not here today can watch it. And with that, I'm gonna let you out a whole 20 seconds early. Actually, I don't have to do all this, but I'm gonna say, Gang gesund. Remember, that's Yiddish for going to hell. Gang gesund. I'll see you tomorrow at 2 o'clock. Bye now.